All right, class, let's continue with finding antiderivative of exponential and logarithmic functions. So same as we separated a little bit for the derivatives, we separating so it wouldn't be so much in one section, but we want to add on. So we just want to be adding on the rules for antiderivatives of exponential, not any, but just the natural exponential and logarithmic functions. So same as with the derivatives, we only looked at the derivative of e to the x and ln of x, so the natural, exponential, and logarithmic functions. All right, so here are the rules. Okay, so natural exponential function, if you have, or you want to find the antiderivative of e to the x, that's just e to the x. Why? Because simply, if you took the derivative of e to the x, what did you get? E to the x. So it stayed the same. It's the same when you go backwards, right? So the antiderivative of e to the x is itself. So as easy as that. Now, sure enough, we immediately went to an e to a function of x, right? So composition of two functions. We have not talked about the chain rule backwards for antiderivatives, right? So we haven't done the product rule backwards. We haven't done the quotient rule backwards because those are really complicated. As a matter of fact, just at the end of this chapter, 5.8 is the chain rule backwards, and 5.9 is the product rule backwards. So for now, we're not dealing with compositions of functions. Those are going to be, again, much harder to deal with, and we're going to do that at the end of this chapter. So for now, actually keeping it a pretty simple one function at a time thing. However, there is one, at least composition of function, that's going to be used a lot. If you remember also from our applications to the natural exponential function, right? So you had some PERT formula, e to the RT, so 0.05 t type of stuff. So what we want to be doing is we want to be dealing with not just e to the t, we're fine e to the x, but some number times t, because most of our applications really had this type of exponential function. So just the coefficient, right, added into this x, not x squared, not 5x squared minus 7x plus 2, but just a number, a constant times x. This is the formula for that. So the antiderivative of e to some number times x is you just have to divide by that number. So it's e to the, it stays as itself, right? But just dividing by that coefficient. So let's just take it really quick. And what if you had a derivative? And maybe, fine, I'm not going to make it a general a, but just let's say 5 times x or 0.05 times x. What was the derivative of this? So it had to at first stay the same, but then you went times, and you took care of the derivative of the exponent. So the derivative of 5x is just 5, yes? So now, sure enough, the antiderivative, what am I going to do? I'm going to keep it the same, but instead of multiplying by this 5, I'm going to divide by it. Okay, so it's the backwards process. So again, this rule here only works when the exponent is a multiple of x, is some number times x. Okay? So it doesn't work for other types of functions of x, like square root of x or x to the fifth, right? Just some number times x to the power of 1, right? That's basically what it is. Okay, so remember also in 5.1 I said we talked about the exception to the rule of the power rule, right? To the power rule. And we said when your power is a -1, we cannot use, that was our exception. We already went over it, but we'll go over it again. Cannot use the power rule. Why? Because the power rule would say what? The antiderivative of x to the -1 is x to the 1 more than that divided by that exponent, right? So you'd end up with an x to the 0. 1 more than -1 would be 0 divided by 0, and this is undefined. So this does not work, right? So there's no answer for that. So when we see an x to the -1, we need to think, wait a minute, what does an x to the -1 also look like? It looks like a 1 over x. Where have I seen a function whose derivative was 1 over x? Well, the derivative of the natural log function is 1 over x, okay? So here are our two rules. The antiderivative of e to the x is itself, yes? The antiderivative of 1 over x is ln x, of course plus a k, right? But I'm just saying those were the two rules that we learned in chapter 3, and let me write them out one more time for you. What did we learn? That the derivative of e to the x was e to the x, so fine, going backwards is the same. And the derivative of ln x is 1 over x. So now we're just looking at the rule backwards. All right? Okay, so let's just practice on it. So I didn't write any problems down. I just make them up for you. Sometimes it takes more to type these than to just quickly write them down. So I'm just going to add in these two new rules, and I'm going to ask you to find the antiderivatives. All right. Okay, or the definite integral. So what's the antiderivative of e to the 2x? Well, the antiderivative of e to the 2x, the rule says, is itself divided by that extra coefficient. So 1/2 e to the 2x plus k. Okay, I'm going to put it in the front, but obviously we kind of start backwards, right? With stays the same, and then let's see if there's anything else going on. Okay, so this might be a problem that we have to come across to find the antiderivative of 1000 e to the 0.06 t dt. And sure enough, most of our natural exponential functions deal with time. And so the variable name will be called t. So this is also why you see this is important, because this here tells me the name of my variable, right? If I'd say that dx, the answer will be a constant, right? So this would just be a constant because the variable apparently is called x and not t. So that's the name of that variable there. Okay, so what do the rules of antiderivative say? It says if you have a coefficient, you keep it. Yes. So the 1000 stays. If you have an e, you keep it. And well, also I like to write it over. And also what? Divide. I'll write it over. That's how I like them. And also divide by what? The whatever coefficient, instead of multiplying, right? When you take the derivative, you go on and multiply by that coefficient. Now you divide by it. So sure enough, that's not going to be 1000 divided by 0.06 is not a nice even number, but here it is. Okay. All right, there's your answer. Okay. And again, this number here came from dividing 1,000 by 0.06. Okay. What about this? Okay. So this almost looks like the problems we just did, right? Except for there's maybe one thing that should stick out to you. And that thing should be this 1 over x. So let me just rewrite this. So one thing, one more time, you might be tempted to do this. You might be tempted to rearrange, of course, we've already talked about that if you want to use the power rule backwards, you better make these look like powers. So finding the antiderivatives of this, so I'm just going to tell you how you might run into trouble, because I'm sure you will remember this one, forget this one rule, or you won't remember it, that's what I meant to say. So according to what we just learned in 5.1, this is an 8 times x to the what? That's a power of 1, so we'll make it a 2 divided by 2 plus x to the, that's a negative 1, so what do? We increase it by 1 and then divide by that, whoopsie daisy, minus x to the negative 2 plus 1 is negative 1 and divide by that. And all of a sudden, we end up with something we're not so sure what to do, right? So that means that was not a good idea to turn the 1/2 or 1 over x into an x to the negative 1. And that should remind us that there's one exception to the power rule. And what is that exception? That 1 over x is not to be taken the antiderivative of using what? The power rule, but rather than the antiderivative of 1 over x is what? ln of x. Okay, and remember what I said about the absolute value. I said that in the 5.1 video. The absolute value was there. Why? Because we do want to make sure, let me write it one more time here. The absolute value is because only positive numbers can be inside a log. And we are not told what kind of a variable this x is. We know x is not 0 because you can't have a 0 inside the log either. And we know x is not 0 because we have a 1 over x. So from the beginning, that simply means x better not be 0, yes? And then, as I said, but we also need to make sure that we're putting positive numbers inside. Okay, so this is our answer. Our answer is 4x squared plus ln of the absolute value of x. Don't forget the absolute value. And then it's a plus, and then again, because the minus and the minus makes a plus, and then what do I do about the x to the negative 1? I'm going to turn it into a 1 over x. Now, that doesn't mean you should move on and make this into an ln of x. Why? I'm not asking you to find the second antiderivatives. We're not doing double integrals, by the way, in this in this course. You would in calculus, same as we find a second derivative, you can find a second antiderivative by putting 2 integral symbols right next to it. We're not going there, okay? Just the first, so just one of them. So just because you see a 1 over x, and I'm bringing this up because it's a common mistake, just because you see a 1 over x, it doesn't mean it turns into an ln x. Why? I'm not asking you to find its antiderivative, right? This is done. Okay. So let's see another problem here. I have this. Here it is. Find the integral of 3e to the 6x minus 1 plus 4x to the negative 1 minus 3 cube root of x squared dx. That seems like a good mixture of exponential. By the way, that's a log. And this is stuff we did in section 5.1. So I'm going to rewrite this for you. So I'm copying this integral. I'm not yet taking the integral. I'm making this prettier. What am I to make prettier? Just to make it clear, the x to the negative 1 is a 1 over x. Okay, so this is the one where the power rule does not work on. Okay, so you will have to train your mind to recognize this one. And then the other thing, really, again, I could have left it and known that's an ln of x when I find the antiderivative. But definitely I needed to fix this. Make it a power, and that's the power of 2/3. Okay, so let's find the antiderivative and then simplify it. So it says keep the coefficients, e to the 6x, but then divide by 6 or multiply by 1/6, minus. The antiderivative of 1 is 1x, yes, because again, the derivative of x is 1, plus 4 times the antiderivative of 1 over x is ln of the absolute value of x, minus 3 x to the, I'm going to increase this 2/3 by 1 and then divide by that exponent plus some kind of constant. Okay, so I'm going to fix this up some more. I have room here. 3 and 6 do reduce to a 1/2 e to the 6x minus x plus 4 ln of the absolute value of x, but this is another thing I need to fix. Let's see, I don't want to rewrite the whole thing again. I don't have room. 2/3 plus 1, that's what? 5/3, yes. And to divide by 5/3 is the same thing as multiplying by what? 3/5. And what is 3 divided by 5/3 is the same thing as 3 times 3/5, which is 9/5. X to the, and that's 5/3 there. Okay. I squished myself down here. All right. Okay, so maybe let's try one more or a couple more. Here it is. Find the antiderivative, and I believe, let me see, that's number 5. Of 4x squared plus 1 times 2x minus 3 over 2x squared dx. So that looks like trouble, and it looks like trouble. Why? Because it looks like I have a product and I have a quotient, and I don't know, there are no rules for antiderivatives of either one of them. So here comes algebra. And what does the algebra do? The algebra tells us that we know how to multiply binomials. So when I multiply this out, I'm going to get an 8x to the 3rd minus 12x squared plus 2x minus 3. Okay. There comes algebra also and tells us that we know how to divide a whole bunch of terms by 1. We just have to divide them under each one of them. So, and again, maybe it's up to you how many steps. Here, I'll write it out. So I'll distribute that out. So, simplifying, reducing each of these fractions. What do we get at first? That's a 4 and an x. Oh, that's like something we know how to deal with. Minus. The x squared completely goes away, and I'm left with a 6. Plus, be careful here. The 2's go away. The x's go away. Where is there an x left? Where are there more x's? Sure enough, on the bottom, right? So x over x squared is 1 over x, right? You have an extra x on the bottom. Minus 3 over 2, and I already know I'd be running into trouble if I'd leave this x squared here on the bottom. So what am I going to do with this x squared? I'm going to put it right next to this 3/2 as a -2 exponent. Okay, why did I not mess with this and write it as an x to the -1? Because this look of 1 over x is more familiar to me, and I know what its antiderivative is, because that's exactly what we're supposed to do, find the antiderivative. Okay, so what's the antiderivative of 4x? Is 4x to the 2 over 2 minus the antiderivative of 6 is 6 times x plus the antiderivative of 1 over x is ln of x, absolute value, minus 3/2 x to the -2 plus 1 is -1, by the way, but I'll write it out for you. Okay, so that's a 2x squared minus 6x plus ln of the absolute value of x. Ooh, that's a -1 times this other negative makes it a positive 3/2 x to the -1. I'm not going to rewrite the whole thing for it. Again, this is an x to the -1, and what do I do with that x to the -1? I put it on the bottom, right? So that's why that becomes a 3 over 2x. Okay, so quite a bit of algebra and a little bit of calculus, but mostly, as you see, it's algebra. Okay. All right, so I have a couple of wordy problems as well. These ones deal with exponential and logarithmic functions, but it's the same exact problems that we did in 5.1. So let's knock these out quickly as well. Marginal cost is given. So what does it mean that I'm giving you the marginal cost? That means I'm giving you the derivative. Yes? And it says find the equation of the cost function. So if I want to find the cost function out of the marginal cost, means to find the antiderivative. Okay. So the cost function is the antiderivative of the marginal cost. Okay. So it's the antiderivative of 60 e to the 0.06x dx. Okay. How do I find the antiderivative of that? Well, it says keep the 60, keep the e, but divide by the coefficient of x if it should have one. Okay. And 60 divided by 0.06, that should be 1,000. Yeah. Okay. So, same as in the problem we did in 5.1, is there a condition here that allows me to find this specific constant k for this problem? Yes, sure enough. So it says the fixed costs, in other words, what? At 0, yes, when 0 items have been produced, the costs are 1,000. So C of 0 is how much? 1,000 e to the 0.06x plus k, and that's supposed to, times 0, x is 0, yes. And that's supposed to come up to equal to 1,000, yes. So out of this, I should be finding the k. However, it's slightly different. Doesn't mean k is 1,000 in this specific problem, because what is e to the power of 0? That's what this one turns into. 0.06 times 0 is 0. What is e to the power of 0, though, equaling to? E to the power of 0 is a 1. right? The other ones were polynomials. Once you plug in a 0 to the third and a 0 to the 1/5, those were zeros. But e to the 0, the exponent this time is a 0. E to the 0 is a 1. So because of this, k turns out to be 0 for this problem. So what is my cost function? My cost function is 1000 e to the 0.06x. Plus 0 have you, but plus 0 is itself. So there you go. So sure enough, let's test it. Let's plug in a 0 into this function. What happens if you plug in a 0? You get 1000. E to the 0 is 1, which is 1000, right? So the fixed costs are 1000. So it works. Okay. So one more. Remember, we had the value in the account that was growing at a rate of, this one says the child is growing at a rate of, and here is the function, right, the rate. Inches per year. Okay, so we know the growth rate. So if we know the growth rate, we know the derivative. Inches per year. What we want is the total inches, right? Find the equation that describes the height of the child at the age of x. So we want to find the antiderivative. Okay. So the height, whatever, make it a function if you want h of x. Again, maybe since it was time, I should have put a t variable rather than an x, but it says h of x, so the height at the age of x is the antiderivative of its growth rate. So that's a 30 times x squared over 2, and by now, plus we know what section we're on, what's the antiderivative of 1 over x? It's the ln of x. Sure enough, I can fix this a bit. And there it is. Okay. So what else do I know? That the child measured 24 inches at the age of 1 year. So what does that mean? The child measured 24 inches at the age of 1 year. So the height at the age of 1, right, at 1 year, was 24. By the way, I couldn't put you a 0 because you can plug in a 0 for inside an ln. So that means that what? What is h of 1? H of 1 is 15 times 1 squared plus ln of 1, yes, plus k. So that's 24. So that's a 15. What's ln of 1? Well, by the way, ln of 1 is equal to 0. So sure enough, 15 plus k is 24 minus the 15 over, so k is going to have to be specifically 9 for this problem. So here is my function. The h at the age of, the height at the age of x was what? 15x squared plus ln of the absolute value of x plus 9. All right. That's the function, right, that predicts the height of a child at the age of x. So now it says, take it a step further, to use this function to predict the height at the age of 4. Okay, so what do I simply have to do? Plug in 4 in here. So, let's see, I'll put this really quick in my calculator. 15 times 16 plus 9 plus, I need an ln of 4. This might be a funny number. 250, yeah, inches, which divided by 12 makes this kid 20 feet. So makes no sense. I better mess with these numbers and make it a little bit more believable for the height of a child. It won't be 20 feet by the age of 4. All right, but we're done.